candidate for Herceptin or through a series of proxy tests. But this woman, Elaine Mardis at Washington University, got a sequencing machine at Washington University, and she found a way to go and sequence individual cancers for about $30,000, and the price is dropping all the time. And she can do it quickly as well, which means that she can begin to go and tailor cancer treatments for individual patients. We often talk about personal medicine, right? But by and large, when you actually press upon the physicians and the researchers who are working on personal medicine, they'll sheepishly admit to you that it doesn't yet exist. Well, here's personalized medicine as a reality right now. I lost my mother to colorectal cancer last year, and we struggled through months and months and months of trying to optimize the best adjuvant treatment for her. If we'd had this, perhaps she might have been saved. So the impact, as I said, better treatments, and the speeding, crucially, a toolkit to go and create new drug therapies as well. So another technology, solid-state batteries. So this is a car problem mainly. So electric hybrid vehicles will never be more than a fraction of the vehicles on the road without better batteries. And that's because they're using lithium-ion batteries with a liquid electrolyte. And as I imagine some of the people in the room know, there are an enormous number of problems with liquid-based lithium-ion batteries, not least of which is that they have to be cooled, they get hot very quickly, and they explode if they're crashed, which is not really what you want in a vehicle, right? So what we'd want to do is to create a solid-state battery where you could remove about half the cost and the weight of a liquid electrolyte and replace it with a solid. So this is interesting. So either it, depends how you want to do it. You could either halve the cost of a $10,000 battery in a car or double the range. But at the moment, by and large, electric cars are a niche and a marginal application. And Anne-Marie Satchery at Stactis, I believe it's pronounced, Stactis, has created a new model. So if this happens, we believe that electric hybrid cars will become much more prevalent, and perhaps will begin to move into other uses as well. Homomorphic encryption. This is a business-to-business problem. So the problem is that many organizations won't use cloud computing because of the security risks involved in placing decrypted information into the cloud. So the cloud's obviously going to be huge. Cloud computing is clearly the next paradigmatic change in computing after microcomputing, personal computing, and then client-server. But if we're honest, at the moment, cloud computing is used largely for applications that are not enterprise scale and are not enterprise critical. And that's because once you get the encrypted data into, say, Amazon's web service, it has to be decrypted to be manipulated. Homomorphic encryption is an old idea. It's about 10 years old, but it's only been made to work in limited settings. This gentleman, Craig Gentry at IBM, has found a mechanism to make homomorphic encryption work at an enterprise scale. For those of you who are either MIT fans or MIT alumni, he's an MIT alumni as well. The mathematics are too complicated to describe on stage. Go to technologyreview.com online and you can read how it's done. But the essential idea is that the data is manipulated in the cloud without it ever leaving an encrypted state and without any degradation of the data. So the impact, I think, is huge. Cloud computing has tremendous advantages over any previous form of computing we've had, not least of which is it makes computing into a, if not a commodity, into a thing that can be on demand. It can become a utility, which has tremendous advantages in terms of costs and efficiency. Cloud streaming. Here is another 10 technology of the year. So the problem is that mobile devices just simply aren't powerful enough with their internal memory and their internal processing to really do some of the heavy-duty streaming that you might want to go and do. There is a solution, though, from Steve Perlman of OnLive. He uses video compression technology and essentially abandons buffering so that movies and quite difficult resource-heavy applications can be streamed directly to devices like an iPad. And if I press this, I think I have a movie.
One of the most advanced applications that you can run today on computers are visualization applications made by companies like Autodesk. This is Autodesk Maya. Autodesk Maya is one of their most advanced packages. It's used for motion pictures, video games, and other places where you're doing typically character animation. You can't run Autodesk Maya on an iPad. You can't run it on a laptop, not with all the features we got here. You need an extremely high-performance computer, and that's, in fact, what we have in our data center. But here it is. I have the full generality of touch and flexibility.
So that was happening in real time. He was manipulating it on the screen, on his screen, but in fact, it was being processed back in the cloud. This means that a whole range of applications that at the moment you simply can only use on a desktop will be available to you in real time. And I think that's important because it means that the impact is that computing could become like electricity. It could become something which is invisible but ubiquitous in the world. Crash-proof code. So we're all sick of our computers crashing all the time, right? And we also somehow take it for granted. And to me, that's an amazing thing, right? Because the critical software has bugs and can crash is an extraordinary thing. We've created this technological civilization on the back of a series of systems that break. You expect your bridges not to fall down every 100 years. Planes aren't allowed to fall out of the sky, and yet we run some of the most important systems we have on things that crash all the time, that they wouldn't even load. And the reason is because software engineers simply didn't have a good mechanism to test large-scale systems. Well, this woman, June Edrondic, at NICTA, which is the Australian government's IT research center, has done some very, very interesting mathematical work to create microkernels inside systems that don't crash. It sounds geeky, but the impact is serious. It means that people don't die. It means that we can begin to embed microcomputers, embed systems in a whole variety of things that we don't want to crash. So this idea that I just alluded to, the idea that information will become ubiquitous, that sensors will be embedded everywhere, if we're going to do that, we better have systems that actually work. So this woman has used a process called formal verification, which previously could only be used for hardware, for chips, which essentially creates an abstract model of hardware. She's applied that to software too. Separating chromosomes. So the problem is fairly significant. Conventional sequencing technologies ignore crucial biological information. And the crucial biological information they ignore, amazingly, is that each one of you in the audience has 2 chromosomes. I know this is extraordinary, but whenever we do genome testing now, we abstract the genetic information and assume a single chromosome. But of course, we've all inherited a chromosome from each one of our parents, and doing so creates an entirely false picture of our genetic makeup. The solution is a very interesting technology that spent a decade or so wandering around looking for an application. That is a microfluidics device from a company called Fluidigm, which was founded by Stephen Quake of Stanford. Microfluidics essentially treats liquids at a molecular level as if they were electricity, as if they were electrons. That's a very, very small chip there. It's an extraordinary technology.